for inviting me such a nice meeting in a wonderful place, Natal. Actually, this is my first visit in Brazil after the 36 hours flight. I'm very tired. So, okay. Today's my talk is about the interfacial effect on the high temperature superconductivity in iron selenide, which is investigated by the dual functionality of the electronic double layer transistors. I am Tsutomu Nojima from Tokyo University. Okay, this work is a close collaboration with Professor Tsukazaki's groups in the same institute, especially Dr. Shiogai and Mr. Miyakawa and Mr. Ito are the main player of this work. This is the outline of my talk. First, we briefly introduce ion-based superconductor, high-temperature superconductivity in the wine cell iron selenide, and then multifunctionality of the electric double layer transistor EDLT. After showing the experimental details, I will discuss our recent result of effect of interface on the high TC superconductivity based on the thickness and the substrate dependence of TC and Hall coefficient. And then we'll discuss also upper critical field of these systems. Among the numerous number of the iron-based superconductors, iron selenide with a TC as high as 9 Kelvin has the simplest crystal structure without blocking layers. However, this simple structure compound has various new phenomena fascinating the many researchers. One of the most exciting and attractive phenomena of this system is its high TC superconductivity in the thin film forms, which was first discovered by the Professor Shue groups in Beijing 5 years ago. As I said before, the TC of the bulk of this compound is as low as 9 Kelvin, but if they make the wine cell film on the strontium titanate by MBE, TC rises up above 40 Kelvin. Right-hand panel shows the first data of the tunneling of the one cell and the 2 unit cell films. Only one unit cell film shows a superconducting gap at low temperature, which corresponds to the 2 delta equal to 40 millikelvin. And on the other hand, in the ex situ transport measurement, TC decreased to the almost 40 Kelvin, but which is still much higher than the bulk values. Just after this discovery, the electronic structure of the wine cell is also investigated by the ARPES measurement. This picture shows the comparison of the film surface of the non-superconducting and superconducting samples controlled by the UHV annealing. Most striking feature of this superconducting sample is the disappearance of the whole pocket at zone centers and appearance of the electron film surface at zone corners. Okay, so this means that the electron doping is the most important in these systems. And they also investigate the gap structure using this ARPES measurement. At low temperature, the gap size is almost same as that of STM, and the gap closing temperature is almost 65 kelvins, which again is higher than the transport data. Okay, as the origin of the high temperature superconductivity, charge transfer from the substrate and strain, tensile strain effect, and the electron phonon coupling with the high frequency phonon of the strontium titanate have been predicted. All of these candidates are based on the characteristics of the strontium titanate, which seems to be natural that the strontium titanate has been believed to special substrate until our experiment. However, in order to find the essential conditions to high TC superconductivity, we should check the importance of the strontium titanate and importance of the wine cell thickness and relationship between the resistive transition TC versus gap closing temperatures. So to investigate these issues, thickness and the carrier tuning on the different substrate is necessary, and we notify that the electric double layer transistor EDLT satisfies our requirement. EDLT is a kind of FET where the unique liquid or electrolyte are used as a gating materials. By applying a few volts, this can accumulate more than one order of magnitude carrier density than the usual FET. And this function is this is a famous function of the EDLT, that is electrostatic doping. Okay. On the other hand, this EDLT device has another functionality that is electrochemical reactions. When the applied VG is larger and temperature is larger than the condition of the electrostatic doping. Okay. This electrostatic reaction contains many phenomena such as electrochemical etching and intercalations and oxygen injection and so on. And in the case of iron selenide, we found that this electrochemical reaction can be used as a very fine etching tool, okay, based on the weak layer coupling due to the van der Waals coupling. Okay, so now this EDLT is a convenience tool with the dual control of the electric structure and thickness, like a double-edged sword. Okay. Oh, sorry. So in order to clarify the essential condition of the high temperature conductors, high temperature superconductors, we tried to induce the superconductivity by etching and doping. Okay, and then we examined the interfacial effect using the different substrate. Usually, the physics of the very thin film has been studied by using the bottom-up method like Institute MBE, like this. But in this work, we address this same subject using the alternative top-down method, using the EDLT, like this. The advantage of this method is that we can do the thin film fabrication and carrier doping in using one sample with in-situ transport measurement with decreasing thickness. Okay. Samples in this work is prepared by the PDL deposition method on the strontium titanate and MgO and potassium tantalate substrate, followed by the post-annealing in a vacuum. As shown in this X-ray diffraction patterns, so we can obtain the completely C-axis oriented films for all the substrate. Okay, and as shown in this magnified figure around the 001 peaks, we can obtain the clear Raoult fringes. Okay, like this, implying that our thin film is very flat. And also from these fringes, we can estimate the thickness very correctly, like this. Okay, and using these film, we made EDL devices like this using the unique liquid DMI, TFSIs. Okay, and and this is this figure shows our experimental scheme showing the relation between the gate bias voltage and temperatures, where the boundary between the blue electrostatic region and red electrochemical etching region is located like this. Okay. And after many preliminary experiments, we finally found that at 245 Kelvin with 5 volt, very slow etching start around here. So we use this temperature for decreasing the thickness. On the other hand, at around 220 Kelvin, this etching event completely stopped, and only the electrostatic charging is possible. Okay, and And the most important parameter in this work, the thickness. The thickness is estimated by assuming that the decrease of the thickness is proportional to the charge amount, which is derived by the temporal integral of the leak current, Ig. Okay. After many experiments, as shown following, we also we check that this relation is very reproducible. So the thickness parameter in the following data is reliable. Okay, let's go to the data. So first, I would like to show to the evolution of the resistive transition by etching. Okay, this is a typical example of the resistance versus temperature curve as a function of the thickness on the strontium titanate substrate. Okay, in the initial 13 nanometer thickness, the TC onset around 9 Kelvin is almost same as the bulk values. But with decreasing thickness, transition becomes two-step, and around 10 nanometers, it changes to the one-step transitions, meaning that the superconductivity developed in the whole samples. Okay, and with decreasing the thickness furthermore at 0.6 nanometer, which corresponds to the 1 unit cell, maximum TC with the onset above the 40 Kelvin occurs. So this implies that our top-down method is working very well, which reproduced the previously reported bottom-up method. Okay. Surprisingly, we obtained the similar type of result in the substrate of MgO and also in the potassium tantalate. Okay. So these results indicate that the strontium titanate is not a unique substrate to obtain the high temperature superconductivity. Okay, and here we note that the critical thickness with a single transition around here is much higher than the 1 unit cell thickness, and this value is depend on the substrate, and which we will discuss later. Anyway, these results mean that the electron doping by the electric field from the top surface and by the charge transfer from the bottom substrate is directly related to the high temperature superconductivities. Okay, in order to check this scenario, we perform the Hall effect measurement. These are the data set of the temperature dependence of sheet resistance and field dependence of the Hall resistance. Okay, and in the thick non-superconducting regions, we obtain the positive slope of the Hall resistance, implying that the main contribution of charge carrier is a Hall. Okay, but with decreasing thickness, we can obtain the high TC superconductivity again, and at the same time, the slope of the Hall coefficient decrease and changes to the negative slope, okay, implying that the conduction carrier changes to from Hall to the electrons. Okay, and by plotting the onset TC as a function of the thickness, we found that there is a three kind of thickness regions. First is a very thick non-superconducting region with a positive Hall coefficient. And in the middle thickness region with 30 Kelvin superconductivity, but with still a positive Hall coefficient. And finally, in the thinnest regions with a 40 Kelvin high TC with a negative Hall coefficient. Okay. These regions can be intuitively explained by using the carrier distribution in our samples. In the thick regions, the electron-rich layer from the top ion gate and from the bottom charge transfer occurs like this, but in between, the bulk-like region with the Hall carrier disturbs the long-range ordering of the superconductivity. But with decreasing thickness, the two electron-rich layers can couple due to the proximity effect. And so in here, we can obtain the superconductivity, single transition superconductivities. But still in between, there is hole regions resulting in the very hole coefficient with small slopes. And finally, in the thinning below the 4 nanometers, the electron-rich layer covers all samples. In this case, the high TC superconductivity with negative hole coefficient occurs. Okay. And the similar result trend is also observed for the MgO and potassium tantalate with the appearance of the high TC superconductivity followed by the sign change of the hole coefficient. Okay. But here we note that the critical thickness for the single transition is smaller for the MgB2. MgO, okay. MgB2 is different. And larger for the potassium oxide. Okay. This can be very clearly seen by plotting the onset temperature and the hole coefficient as a function of the thickness. Okay. For both cases, the critical thickness of the single critical transitions and critical thickness for the sign change of the hole coefficient increase with increase in order of the MgO, strontium titanate, and potassium tantalate. Okay, and you know that the slope of the hole coefficient is almost same irrespective of the substrate materials, implying that only this middle bulk region decrease by etching. Okay, and by assuming that the thickness depression layer, accumulation layer from the top ion gate is almost 3 nanometers, we can easily calculate the charge transfer layer's thickness. Okay, and that is 0 nanometer for MgO and 4 nanometer for strontium titanate and 13 nanometer for potassium tantalate. Okay, and this the difference in substrate can be explained by the interface configurations of the barrier of the 3 kinds of the substrate. In the case of strontium titanate, oxygen defect on the top surface causes the electrons, and this can transfer to the iron selenide. This is the origin of the minus cell of the high TC superconductivity. And in the case of potassium tantalate is one of the polar materials with plus charge tantal O2 and minus charge potassium oxide. So at the top surface, the distribution of the charge, electron charge result in the charge transfer of the to the iron selenide, as shown in the previous speaker and LAO-STO. Okay. And however, in the case of MgO, the surface is very stable. There's no oxygen defect, and so there's no charge transfers. So in this case, the high TC superconductivity is induced only with the electric field from the top gate. Okay, so okay, and there's no time. And by plotting the onset temperature as a function of the hole coefficient at 50 Kelvin, we obtain the universal relation, which independent of the substrate material and also thickness. Okay, and in the case of iron selenide, which is a compensated same metal, hole coefficient is not directly related to the charge carrier density, but we think that this whole coefficient is reflects the average carrier density of the in the same film. So this universal relation implies that the superconductivity can occur by the carrier balance between the hole and electrons, and not occurs by the electron-phonon coupling. Okay. Finally, I would like to show you the upper critical field of these systems. And these figures show the temperature dependence resistive transition in the magnetic field for the 40 nanometer, 8 nanometer, and 1 nanometer iron cylinder samples for the out of plane in plane configurations. In the case of 40 nanometer with the bulk TCs, the resistive transition is the width of the resistive transition is almost same orders with an anisotropic parameter of almost 2. But on the other hand, in the thin regions, for these two samples, the transition width is very anisotropic. And you can notice that in parallel conditions, the transition width is not so different between the two thicknesses, implying that the upper critical field is not determined by the thickness only. Indeed, if we plot the upper critical field as a function of temperatures, data is something like that. And from this data, we obtain the in-plane coherence length of the 2 nanometers. And using this length, we obtain the C-axis out-of-plane coherence length of almost 0.2 nanometers, which is much smaller than the length, C-axis length. This situation is very similar to the situation of the Q plate, where the Cooper pair is confined in the 1 layers. Okay? Maybe this situation can be related to the high temperature superconductivities. Okay, let's summarize my talk. So in this work, we successfully prepared high temperature superconductivity with a 40 Kelvin TC by electrochemical etching and electrostatic doping. And so we found that the substrate independence and critical thickness larger than the wine cell and TC scaling with the Hall coefficient. These results indicated that the wine cell and strontium titanate is not essential conditions, and electron doping from the top or bottom is a very important, crucial rules. And we also found the out of coherence length is very small, smaller than the C-axis length. Thank you for attention.